Okay, in this problem, we've got a double wheel, 10 kilograms, radius gyration. It's got a spring attached to it with a cord around the inner hub. Release from rest. Spring is stretched 25 millimeters. Um, Calculate the maximum velocity of the center of O during the ensuing motion. So here's the thing. Only thing going on here is springs and gravity. So we're going to use conservation of energy, right? So that's going to be KE1 plus PE1 equals KE2 plus PE2. Okay, and of course it starts from rest, so that guy goes to 0. So we're going to step through this and determine what's going on. So initially what I'm going to assume, again, I get to set my datum. So I'm going to set the position datum right at 0 at this point. We'll call the due to gravity 0. However, there is an initial stretch in the spring, which is going to be equal to 1/2 k, which is 600 s squared, which is again 0.225 squared. Okay, so that's the initial stretch in the spring. That's what I'm going to call my only potential energy at this point. Okay, KE2 is that final. This is really what we're kind of trying to find, I suppose. Okay, which is the final kinetic energy, which is going to be 1/2 mv squared plus 1/2 I omega squared, right? Because it's going to be rotating as well, where I is m times the radius of gyration squared, which is 0.125. Okay, that is I. And then omega, I want in terms of velocity, because that's what I'm trying to calculate for, is the maximum velocity. So we'll call that velocity over the roll, because it's rolling without slipping here. Doesn't it say that? Yeah, the wheel rolls without slipping. 0.2 squared. So that is the kinetic energy of this wheel that it's rolling. Okay. So now we've got probably the most challenging one, which is the final potential energy. Okay, because our assumption, actually the assumption I'm going to use is that this guy actually rolls down the incline. It could pull it up, we're not sure. We've got to make an assumption. If we're wrong, we get negative answers, right? So what I'm going to assume is it starts here and then ends down here somewhere. Okay? So we'll say PE2. Okay? And what I will do is I'll call this position from here to here X. Okay? Inverse sine gives me that this angle, I'm sorry, inverse tangent gives me that that angle is 11.3 degrees. Okay? So it goes below my datum, so it's going to start with a negative gravity. So that's going to be negative 10 times 9.8 mg, and then h, again, this is below, it's going to be that x times the sine of 11.3. Okay, so that is the potential energy as it rolls down the incline. If it rolls up the incline, then x will be negative, making that positive, right? So two negatives make a positive. So as long as we're consistent, we should be okay with this. Okay. Now I've got the spring, which is going to stretch even more than it did before. Okay. So I have, I've got 1/2 k. Okay. Now it's not just x that it rotates, okay, or that it stretches, right? Because there's some amount, you think about this point right here, it's going to roll around based on how much it rolls. So it's going to be that distance x. Actually, the total stretch of the spring, I'll write it over here. Okay, so the total stretch of the spring on this guy is going to be, remember, it's got an initial stretch, so that 225 right off the bat. Okay, and then it's got the distance x that it travels. Okay, and then we think about the fact that it rolls up, so I need to find that radius times the angle that it rotates. Okay, so the radius that it's wrapped around is 0.075, right? And the amount that it rotates, again, because it rolls without slipping, is just going to be that distance traveled over the outer radius of 0.2, right? So again, we've got the initial stretch plus the distance it travels plus the amount that it rotates up on that spool. Okay, so from that, I can go ahead and plug in then what the stretch of the spring is. It's that total thing, and I'm going to combine the x's just to clean things up a little. So it's going to be the initial stretch in the spring plus it's going to wind up being 1.375. Oops, times x squared. Okay, so that is the new stretch in the spring. That's the final potential energy. Okay, so putting in everything I know, okay, I have basically, PE1 equals KE2 plus PE2. What I get there is I get 15.1875 equals 6.95 v squared minus 19.2x plus 567.2, 567.2 x squared. Okay. Oh, I'm not quite done yet. There's still more. Plus 185.6 plus, that's times x, plus 15.2. Okay, so that's basically setting up that initial equation with everything that I know about it. So I've got this big long equation with v squared in it and x in it. Rearranging this a little bit, basically getting v on one side, I'm going to have 6.95 v squared is going to equal negative 567 x squared minus 166x is the answer that I get here. Okay, so that's an equation that relates the velocity to the position of that sack. Now again, I want to find the maximum velocity. So hopefully you remember that if I take a time derivative, if I take a derivative of this thing, set it equal to 0, I'll be able to find the position where the velocity equals 0. So if I say 0 equals, and again I'm taking a derivative of this, which will be negative 1134x minus 166, right? That is the derivative. Set that equal to 0. Okay. X then equals negative. So I was wrong. This guy actually moves up. Okay. Because I get a negative x. But again, this is the point at which it's maximum. Plugging this guy back into that equation, then I find V max. Maybe I call this X max. Find V max is then equal to 1.32 meters per second. So again, you just set it up, the equation, conservation of energy, okay? Then you solve it down. basically in terms of v and x, and then just do a derivative set equal to 0 to figure out where your maximum velocity is occurring. And that actually occurs at negative x, which actually means it's moving up the incline there.